We'll go and take a look at some hybrid models. So can you folks tell me, do you see a model called gridded system dynamics using AnyLogic 7? Yeah? Okay, I'd like you to open that one up. And this, like most of the previous models we examined, is a decidedly simple model. So this was designed to sort of look at the basic mechanisms involved. The idea here is that we have a set of patches. These patches, if we run the model, these patches are arranged in a grid, and each patch is characterized according to a system dynamic model. Now, there's really sort of little empirical basis for the system dynamics model. This is just one that I created to sort of capture, something that would lead to some interesting dynamics and capture some features that are common in this sort of context. So we have geographical areas, each associated with some population that exists in both immature and mature forms, and the mature forms migrate between different areas that are adjacent. And I'd like to take a look at how this is implemented. You'll notice that this grid square is set to reflect the, I think it's the total number of individuals. It may be the number of mature individuals within a given grid square, okay? Okay, so here's a grid square here, and here we do some interpolation that basically sets the color of this grid square based on the value associated with this. If you're interested in doing anything like this, this gives one idea here. You can set this HSB color. I will tell you this, there's a very nice AnyLogic function called lerp color, L-E-R-P, color, that I'm actually not using here, but which could also have been used. And basically what lerp color does, it interpolates between two colors. So if you have one color, that's one extreme, another color is another extreme, and an argument that goes from 0 to 1, I think. And as it goes from 0 to 1, if it's closer to 0, you have color 1, I believe. And if it's closer to 1, you have color 2. And that can allow you to sort of show a color that's kind of a mixture of two other colors. So lerp color is its name. In any event, the basic gist of it is that we have this population, and each patch, so we have patches, and each patch is characterized by this population, this patch population. And there's this net migration term, which calls off to a function called get immigration rate. And get immigration rate here is set by looking at the relative sizes of this population with neighboring populations. So basically, it considers all patches around this. It should really not be intended like that. I'm not sure why that is. And we go over and get the patch that's next to us, and so go over each of the neighboring patches, and for each such patch, we basically total up the difference between the neighbor's population and ours for mature individuals times some diffusion coefficient. So the basic idea is if the neighboring patch has a lot more than we do of these organisms, they're going to probably come into our patch. They're going to diffuse into our patch. So this might depict something like sea lice, and they're spread within the ocean. They kind of spread via the ocean currents, and if you have a lot of them in one area, they'll tend to diffuse into other areas. So we have this kind of migration coefficient. We total that up over each of our neighbors, and we return the number, the rate at which they come into our patch. So here we have a hybrid model in the sense that each patch defined in a agent-based fashion. This is very familiar territory. If you go to main and you scroll down, you'll see that we're in a discrete environment with certain number of rows, certain number of columns. The agents are arranged. They're placed in a regular grid, and we have no network to speak of, but we do have these agents in cells, and these agents communicate with one another in a continuous fashion. And by communicating with each other, they lead to diffusion of agents, or of these population members from one cell to the other. Each patch remains in a static way at a given place, and neighbors come, populations from neighbors come in, and others die in that patch, and others are born in that patch. So a very simple model where we have a system dynamics model embedded in agents. The agents are arranged in a grid, and we simply have interactions with our neighbors. The one thing I haven't shown you, but is this neighboring patches. The neighboring patches are just our four neighbors, and rather than calling that regularly, I figure out who our neighbors are in space in a toroidal way. This is something I wanted to bring to your attention. Some modeling packages make it very easy to define toroids. The idea behind a toroid is that the space wraps around. But sometimes in agent-based models, where space just ends at a boundary, you get strange effects at the boundary, because at the boundary, for example, the cells have fewer neighbors, and so that there's artificial things that happen, particularly at the corners. A cell that normally is considered to have four neighbors, north, south, east, west, in a given corner, it has two. And so you may see strange artifacts that are not a reflection of the underlying system. They're a reflection of the fact that you happen to be displaying it in this artificially bounded way. And in order to avoid those sort of artifacts, what's sometimes done in agent-based modeling is you create a toroid. It's like a donut. It wraps around from the right side to the left side, and it wraps around from the top to the bottom. And what that means is, for example, this neighbor here that I'm pointing at here, its neighbors are this guy, this guy, this guy, and then this one up here at the top. Okay, this one on the left-hand side's neighbor includes this one over here on the right at the same level. So it kind of wraps around. Think of making a donut of it. This model exhibits toroidal space, and perhaps Priyasri could take note of that. And so we can label this example as exhibiting toroidal space on the site we're building. Yeah. Anyway, not particularly fancy, but the patch neighbors that are deduced in here basically take into account where you are in the space, and they figure out who are your four neighbors, take into account the toroidal character of things. Okay. So here's a bit of code that figures that sort of stuff out. So given that we're in a toroidal way, this is sort of the way we do it. And so if we're a toroid, this is how we figure out our neighbors. Okay? Does that make sense? So if you want to do toroids, AnyLogic doesn't provide a lot of support to them. Last I checked, it had basically no support. Here's some code for you that will do it for you. Okay, it will compute for each cell sort of who its neighboring cells are, and compile a little so-called array of them called neighboring patches. North, south, east, west in this toroidal space. Okay? Very good. I should note, I try to make all these models available for public distribution, and these particular ones I've given you, I'll double check, but I don't, you're welcome to adapt them as you see fit. Okay, Um, Actually, one exception to that, because it is some collaborative, is the Beifeng Ren model. I'll be letting you know of any others that are of concern. Um, okay, so this is one model, very simple idea. Patches in an arranged grid, toroidally spaced or toroidally connected, and system dynamics describing each patch. Very useful, very useful. So every patch is characterized by interaction with four neighbors. So let's close that. Any questions on that? No? Okay. So now to open up a model that's, and by the way, we've used that for, that basic scheme we've used for real life models like geographical areas where we have regions of our province and we want to simulate the change driving certain vector-borne diseases, most notably West Nile within our province, where it has very different dynamics for different regions of our province because of local ecozones. So we divide it up into these patches. That's the basic idea. Okay, so let's take a look at one called CTL state variable using AnyLogic 7. So CTL stands for cytotoxic T lymphocyte, and about 7 or so years ago, about 8 through about 5 years ago, I was doing a fair bit of work in what's called mathematical immunology, and particularly characterizing within a given person, for example, how the infection would spread in terms of viral load, indicated here with V, in terms of uninfected cells and infected cells, indicated in terms of X and Y. And one of the published models in this, which came out of a book by, I think it was Nowak and May, Robert May, Sir Robert May, and then Nowak, was a model that stands before you. So this is a particular model used in their book as depicting an immune system with respect to one particular pathogen. So what goes on here is that at the level of an individual, we have virions coming in from outside. These are these free virus particles. And we have those free virions that have built up then infecting cells. So the cells transition from an uninfected state to an infected state. There's natural cell death that occurs, but also cell death by the immune system. Infected cell death occurs in a way that it actually produces virions. It actually, the cells undergo lysis, they split apart, and these virus particles come out, and that builds a stock of virus particles. Fortunately for our bodies, the stock of virus particles, while it does infect these cells, the presence of infected cells triggers an immune response. We have some quite articulated models associated with immunological dynamics. I think one of which we'd have to be cautious about too, flu immunoepi, which also has some collaborative ties. And in that case, we have a quite articulated representation of the immune system. Here it's very simple. It's a single stalk. So the immune response kicks in, and you build up a stock of immune defenses in the form of cytotoxic T lymphocytes. I think these are CD8 cells, if I remember correctly. There may be CD4 cells. And that stock basically kills off infected cells. So this is what's called cell-mediated immunity. It's an aspect of adaptive immunity, the adaptive immune system. And basically, it's what protects our body once we've gotten infected, as I understand from immunologists. So in this case, what we did, which was fairly novel at the time, I think there was one or two people that had also done a similar thing, although we didn't know about them initially, is we had hitched up these individuals into networks, okay? So we placed these individuals in a network whereby virus could be received from the network. And this is the coupling right here. So we have omega, the flow in of virions from neighbors is some very small constant omega times the total viral load of neighbors. And the total viral load of neighbors is calculated via function, total viral load of neighbors here. And basically it's just looping through each neighbor. If there's no neighbors, we have zero viral load there. Otherwise, it loops through each neighbor and it totals up their viral load and returns the sum of that. Okay? So here's the viral load from neighbors, and it's flowing into me as a person. Okay, so that's what leads to the sort of buildup of free virus within this system. Now, within this context, though, we don't purely have a model of an SD, although this is a key part of it. This drives the key dynamics. The other piece we have is a state chart type model, and the state chart model has a transition type that we have not used much, but it's a condition type. And basically what it says is if the free virus level within this individual, this is within an individual, if it is greater than a threshold, then this person will die and will be, and at time of death, they'll be removed from the population. Okay? So we've seen that basic mechanism before, removal from a population, and this will check if that indeed happens. And by the way, you can see why I thought that would work, that condition elsewhere. And it makes me wonder if it would work in the context of a state chart, what you were asking about before. We'll have to come back to that. Serious? Sorry. The thing you were asking about. So here we have a condition. When a certain condition is reached, we specify it declaratively. We just say when this certain thing happens, namely when the free viral load is greater than this, then a person dies and they're removed. So what does this lead to? Well, if we have a very high viral load threshold, what we see is individuals, in a familiar way, if you go up to Maine, people are placed in a network that is randomly distributed and with a distance-based connection with this spacing. Okay, so they're scattered randomly around the space, and they're connected in a distance-based fashion. So two people are connected if and only if they lie within this distance of each other, right? So let's run this model here. This model, the existence of this model and other models like it was motivated a lot by trying to understand the impact on spread of infection in a population of heterogeneity in immunocompetence and the ability to fight off an infection, and the impact of possible treatment strategies in blunting the immune response. The idea is some people have posited, based on immunological evidence, that if you treat people too quickly, everyone agrees, treating people not quickly enough is really bad, particularly for STIs like chlamydia, which we were studying. It can cause severe reproductive damage. But what's the controversial idea that was advanced was that maybe we're treating people too quickly. By bringing them in for treatment, their immune system is not getting a chance to build up immunity. We're treating them quickly, and then we're throwing them back in their sexual network where they're going to catch chlamydia again. They're going to catch it maybe from whoever gave it to them the first time. So we treat them, we throw them back in, they're going to get it again. Maybe it's better for them to build up immunity. Because after all, each of us goes around with not only the public health system protecting us, but our individual health system, our health system that's based on immune response. And so we were interested in trying to understand the way in which immune response was affected by treatment and the ways in which that would affect the spread of infection throughout a population. So here we see an infection spreading across the population. and it may be particularly serious in individuals with low immune strength. So there's a variety of individuals here depicted, and some individuals within this population are associated with higher immune strength than others. So if we look at the characteristics of the population, I'll stop this for a minute. If we go up to the population here, we'll find that people in the population are set up in a heterogeneous fashion, and they're given specifically a variety of immune strengths. And so some individuals have a high immune strength and some individuals have low immune strength. And this is the diversity that we see when we look at the real world. We see a variety of people with a variety of levels of immune strength, and something like flu in the summer lives predominantly in people with low immune strength. It lives in long-term care facilities, hospitals, amongst those with who are taking immunosuppressants because of transplants. And a model like this, by capturing the impact of immune strength on how the infection spreads over the network, could give us insight as to how that heterogeneity may be affecting the spread of real-life infections. This is a more stylized investigation. We had more detailed models for chlamydia and for flu, which we did examine in more detail. So here, individuals are responding to infection. What you see based on the redness is the viral level. The size of this circle is indicative of the strength of their immune response. So the size of the stock of CTLs. And these individuals are infecting their neighbors and then being infected by the neighbors in turn with sort of secondary infections. So these individuals are all associated with these differential equations. The fact that these are staying of significant size is an indication that their immune complement, the set of immune cells set to fight this infection, have been built up by exposure. And that's in contrast to these individuals over here who weren't infected and therefore have low immunity to this bug. So if we were to reintroduce this bug into this left-hand component rather than the right-hand component, it would be a striking difference. It wouldn't spread nearly as effective in the left hand as it would in the right hand. Okay. So, we could go perform that, but time is short. Yes. That's right. So it's modeling the immune system dynamics within a person. So there's a variety of models of the immune system that have been advanced, and they're quite articulated these days. So there's quite a literature on how to model the immune system, and this was based on an early model of the immune system as advanced by two researchers in that area. This is a very simplified model. We have more advanced ones, including one I think I provided to you related to flu that was created by our collaboration with an immunologist. But the fundamental idea here is that within an individual, you have these dynamics associated with exposure to a bug, and that builds up over time more and more bug within you by infecting cells, and those cells release new virus particles. So you have this positive feedback building up these virus particles. At the same time, that same infection, by infecting cells, those infected cells stimulate the development of immune system defenses. And so we are capturing the resulting immune system dynamics here within a person in the context of a network, in the context of interactions in the network. And the key insights that were being sought here were often associated when you have individuals with different characteristics, so a mixed population where you had some individuals with low levels of immune system defenses, like think people in a long-term care facility, in a population where you also have people with strong immune system defenses. How does that mixture affect the spread of infection? And in terms of prioritization of treatment strategies, or prioritization of immunization, or prioritization of of efforts to fight the bug, would that suggest any strategies based on a principled way on levels of immune strength? For example, maybe we should first treat those who are, who have low immunities, or maybe we should try to quarantine more aggressively those with low levels of immunocompetence. These would be different strategies you could examine in a model like this, and you could see its impact on the infection spread in the population as a whole. Because changing immune system strength here is captured in a single parameter. And if you think about a model, let's suppose you create a stock and flow model of this, of spread of infection, or suppose you create a state chart-based model, stock infection. Your immune strength impacts a lot of things. It impacts your likelihood of getting infected in the first place. It impacts how long you have the infection and how likely you are to infect other people. And we could capture those effects all in a very simple way by having this representation of immune system dynamics of individuals who are coupled together. The other thing we could capture in a model like this was, in which we were quite interested in, is the effect of treatment as it affects dynamics within an individual. So again, the idea was for certain types of conditions, which have some similarity to the one depicted here, if you treat an individual early on, it may stop the Y stalk, the infected cell stalk, from growing, which prevents the immune system from building up. And the question is it possible that you could actually adversely affect someone's health in the long term by keeping them shielded from building up their immune response? By treating them too quickly, could you leave them actually in a worse state? And it may sound counterintuitive, but thoughts like that have been advanced in other areas. My colleagues work in public health related factors in Singapore tell me that by treating people by having too pure a water system, they've left their population at greater risk of waterborne infection overseas. Similarly, by sheltering kids too much from bugs, you may actually predispose them to more severe outbreaks later in life when they're more vulnerable to them. And a model like this can help us examine factors like that by capturing the impact of immune dynamics and impact of exposure to infection. So we have a published paper. This particular model led to a paper in 2007, myself together with Dave Vickers, where we looked at a variety of strategies. And not surprisingly, I mean, one of the things it suggested, and this is a very interesting aspect in which people are interested, is waning immunity. If you prevent people from getting exposed, so suppose someone's exposed to a bug early on, or suppose they get vaccinated. If they don't encounter that bug again or get another booster vaccine, their immunity will decay over time, okay? And then if they are exposed later, they'll have a more adverse response. In other words, they'll tend to get sicker because they're not as primed. But if they're exposed to it in little bits over time, it kind of primes them to quickly snuff it out. And so these kind of systems effects that operate at an individual level with respect to exposure that lead to sort of counterintuitive results. It may be that you think you're saving someone from a lot of grief by keeping them from being exposed to a pathogen, but it may be that ongoing exposure confers some benefits because it lowers the impact of that exposure going forward. And so we are putting that into a network context and examining the impact. Yeah. Yeah. In a grid. Yeah. Oh, I see. Yeah, that's right. I mean, in this case here, we had SD used at an aggregate level, and then people were created as agents. But the agents that were created in this model here on the board did not have any SD components in them. The SD was used to capture the aggregate. Here, it's taking that and flipping on its head. You have an aggregate model, which is the agents are at a higher level, and the SD describes the dynamics within an agent.
So that's like the
It's like the grid. Right, but here it's people and networks, but it's people, and this is the thing I haven't shown yet. But if we look at medium viral threshold, if we run that scenario, we'll see that you also have a dynamic population. So you have a population where individuals are removed based on their ability to sort of handle the infection, and if their immune system strength or their network context is such they have an overly adverse exposure, if their viral level goes too high, they're removed from the population. And that also leads to dynamics that are kind of interesting because it shapes the subsequent exposures. So here the network has been cut short. And these are real phenomena. I mean, it's a terrible thing, but elderly within our societies die from flu sometimes. Things that are fairly modest infections that are inconveniences, nuisances to those of us at a younger age can be fatal to someone at an older age. And even people who have kidney transplants and have to take immunosuppressants, they have to be quite careful about exposure to bugs because a bug can really knock them for a loop, and in some cases can be lethal. So here we have the ability to capture that sort of context as well, which we didn't do in that 2007 paper, but which is handily done using this other type of dynamics captured by a state chart. So this is a model which makes use of hybrid modeling both at multi-scale level, but also within an individual. You have sort of state chart type classic agent-based modeling together with system dynamics within the individual. So within a given individual, we can mix multiple sorts of modeling. So are those helpful comments? Okay. Any other questions about this? No? Okay. I think maybe I'll show just one other example here. And I should make sure I'm not missing any. Oh, okay. Uh-oh. Okay. Let me just see. I've got to make sure I'm online here. Got kicked out. Okay. Go. Oops. Not that. Okay. So one other model that I wanted to show you was one that's a hybrid model which incorporates a representation of space and spatial movement. And this is partly triggered by Kristen's question. This model, I'm not sure if I've provided it for you. I'm going to have to go. Oh yes, this is actually another one. Basic Health Economics, ABM, AnyLogic 7. This is actually a different sort of model, and I'm going to have to record that I need to do that. Yeah. Yes. I think it can just be this one. Yeah. It should say refactored. Health Economics. So you don't have to do the so-called refactored one. Okay. So here, let's take a look at what we have. So here you see a model that in some senses are familiar to you, but they may be hitched up in a slightly different way. So here we have stocks and flows within Maine, and these stocks and flows are accumulating quantities of interest in health economics, quality-adjusted life years, life years lived, quality-adjusted life years lived for the population, accumulated undiscounted costs, accumulated discounted costs. So for those of you not familiar with health economics, when we try to assess how to get the greatest bang for the buck, how to use our resources most effectively, often people turn to cost-effectiveness strategies to understand, the degree of gain per dollar spent from different health interventions. And here we have quality adjusted life years as one way of sort of quantifying the health outcomes associated with a given scenario. And we're often interested in comparing that between scenarios, and specifically comparing the dollars required per quality adjusted life year gained, which is a key measure. And there's certain conventions associated with this. For example, associated with discounting at a certain rate, discounting costs, and discounting quality adjusted life years. And there's a whole subfield, that where people will routinely do these cost effectiveness analyses. Cost effectiveness analyses are conducted at very different levels of detail, and dynamic models can be a potent vehicle for delivering on them, but they're sometimes conducted without that, to the detriment of the accuracy, in my view. Okay, so this is all well and good. So we have these stocks and flows, but where do these stocks and flows come from? If we go and we look at quality adjusted life years, we'll see we have a population statistic called. See that? We've done that many times before, right? We asked the population to calculate a statistic. Let's go see where that statistic is characterized. Okay? So we'll go into the population here, right? And let's go down to the statistics area. Here, we have a variety of statistics calculated. You notice this one is cumulative quality of life, and here we're taking the sum across the population of individuals' quality of life. Here, a new cost per year. We have cost per year an item. And when you look at this, it becomes clear item is a person here. So let's go down to person level. So persons within this model are individual agents. They are in a variety of states, and I've just shown this out in a very stylized fashion. And we have variables for quality of life and cost per year associated with that. Where do you think those variables are set? Based on examples we've done together, think about interacting state charts. Where would you wager? Where would you posit that those variables are set? Well, they're actually set within each state. If this person is, say, has type 2 diabetes, we assign them a certain quality of life based on that, and a certain number of costs per year. Now, these numbers are really for demonstration purposes. They're not grounded by the literature. The point is, though, that within each health state, we may specify a certain number of costs per year and a certain quality of life. However, that's not all. You'll notice in this transition to a transplant, there's a different sort of cost. There's a cost per event. So you not only have costs per year being in a health state, you also have costs per event. For example, when a transplant takes place, there's a cost associated with it, say of $75,000. Okay. So here, what we're doing is we're actually incrementing directly that stock that's in main. Hence says get main. This is created in AnyLogic 6, so now we could do, main dot, and we're incrementing that by an amount that's appropriate given the type of health event that's being undertaken here. So here we have costs, both costs per year of being in a state that are being integrated quite literally within our stocks and flows here. You have a cost per year. Flows are some number of thing per year, and if you have costs on the right-hand side here, this stock is going to be measured in dollars, and this will be dollars per year. and this will be literally integrating up over time. The cost per year is totaled up across the population, right? You have person one, they're in a diabetic state, they impose $2,000 per year. Person two is in a pre-diabetic state, they impose $500 per year. Person three is in a normal glycemic state, they impose $0 per year, whatever it is, $200 per year. You total up across all population members, cost per year, and those are a flow into cost. That's how system dynamics models typically work. If we have time unit as years, the flows are measured in cost per year for a stock that's cost. I'll be with you in just a sec. And then the other element of how this model is changed is we have over here a stock, accumulated undiscounted costs, and that's not only affected by those costs per year, it's integrated up over time. It's affected in a direct way by incrementing it when an event takes place. A conceptually sort of an essentially instantaneous event, as it's treated here, like a transplant, directly increments that cost because it's not a per year cost, it's a added cost of $75,000. So we just add that in to that stock in the main model. So here we see a very different situation. We see stocks and flows at a high level summarizing up state of the population as dictated by these underlying agents. And it's totaling up these health economics total. Right. So yes, Rodrigo.
In this case, when you have just one sector, it's easy in certain way to know in which state will be the agent. But what happens when you have three competing diseases with three different sectors?
That's a very good question. So suppose we had heart disease, diabetes, and kidney disease, right? With diabetes being a sort of potent risk factor for the other two. So you're saying, how would you say what are the costs per year? Yeah. What are the quality of life? Yeah. Well, I would say yes, it's messier, but fortunately, there's probably hundreds, if not thousands, of people who do exactly that issue of figure out how to deal with that situation. Who are not per se modelers, but they're health economists, and they've studied that issue. People who work in outcomes research, that sort of issue of how to assess, how to estimate quality of life or cost for people with comorbidities. It's a substantive issue in health economics because we know that particularly in the context of a graying population, that those who have one condition often have others, and we need to be able to impose costs. Yes.
It's better than the alternative of just simplifying and assuming that people can only be in one at a time. Arguably more wrong. So you've got yes, there are data. I mean, this is a great example of this is more accurate to know when people are in the intersection of the different states, because when you have similar risk factors for them, that happens.
Yeah.
You have people with like multiple chronic conditions, and there are implications for quality of life and cost. And yes, so it's more accurate to simulate it this way when this happens than to assume what we often do, that you're only going to go into that first state. It does have implications though in terms of data, but you're right, people slice data.
But I think Rodrigo was probably asking about this thing with the variables. Yeah, I think you were asking about the plumbing. Okay. Okay, fair enough. So how would you add a computation? So in terms of, the issue is not the design, the issue is in terms of implementing it, how would you capture it if you have many state charts? Let's suppose we have perfect data, associated with how a given combination of comorbidities, what costs would be associated with that, right? Suppose we knew someone has heart disease and diabetes and chronic kidney disease, they have this quality of life and this cost per year. And if someone has heart disease, diabetes, and no nephrological problems, they have such and such costs and quality of life. Well, what we would do then is you would have a multidimensional array specifying those things. So it would be an array, and its first index that you would look up might be their diabetes state. The second index would be their heart disease state. The third index would be their chronic kidney disease state, and you would look up for them in that array. Conceptually, it would be a cube, right? It would be something like this if we had those three conditions. And if these were dichotomous conditions, it would be something like this. And you know, this would be, you know, no diabetes, and this would be with diabetes. I'm going to put a bar over it to indicate none. This would be, you know, no kidney disease, and this would be with kidney disease. And this one will be, you know, you have no heart disease and you have heart disease. And each one of these would store a number for quality of life, say. And you could have a similar one for cost per year and look it up. Yeah, and those would ideally come from health economic theory, and I think probably they have. I think probably people have tried to estimate those in the presence of lots of comorbidities from the Framingham study or whatever other study, and certain types of utility measures for, you know, the health-related quality of life utility measures from the quality well or through other elicitation. So yeah, I think those things have been worked on, and as a practical matter, you're right, you wouldn't be directly setting this when you're in a state, oh, I know what it is. Instead, you'd have to look up, oh, I'm in this state for diabetes, I'm in this state for heart disease, I'm in that state for kidney disease, and therefore the number is this, right? But at a mechanical level, it could be done very easily as a result, but it would be a bit different than that. It wouldn't be, I enter the state, I know exactly what it is immediately. I'd have to look it up in this little table. Is that helpful? Mm-hmm. Yeah. So the benefit of that, yeah. Other than helping with the statistic selection, is there another benefit? And it seems like no, in this case, it's you're saying with the hybrid model here? Yeah. Oh no, it's just a nice way of integrating up the different values, the cost per year value, and I was wondering if it tells you anything beyond that you wouldn't be able to do if you were just crunching. Right. I don't think so, but it cleans up some of the calculations. Like you have cost per year. Conceptually, cost is an integral of cost per year, and you don't have to manually in the model, you know, do how long was I in this state, and you know, for how long was I in it, and what's the cost per year of that, and total it up. Instead, it just gets done for you. And so, you know, it's in that sense, it's kind of the right tool for the job. I mean, in case that people haven't noticed, I'm very pragmatic about these things, and you know, it just kind of sometimes it feels natural to use a screwdriver, and sometimes it feels natural to use a hammer, and sometimes it feels natural to use a saw, and I will switch between them when it seems like the elegant way to do it. And often the elegant way is the more transparent way, and the way that's less likely to yield, you know, mistakes, and the way that I can share more readily with others and with stakeholders. And so I tend to use that. And I think this is just a case of this. It takes care of a lot of details that would otherwise be potentially error-prone and cumbersome. Is that helpful?
Yeah. Well, actually, maybe that's just from running it. I'm seeing that you can continuously visualize the cost rather than just having it calculate at the end or dump it out at the
Precisely. I mean, again, when I wore a younger man's shoes, I was kind of skeptical about the virtue of this, but now on just a number of times, I've realized that looking at the columns and numbers afterwards really shields it blocks me from certain insights that I have while I'm interactively, you know, viewing it, and I've learned to sort of view those as fairly important. So where possible, I like to try to capture these things in a way that does afford us ongoing feedback. Yeah. Are those helpful comments? Okay. But the other model I did want to show is this model, and I don't think I sent this because this has it has a collaborative side. But let me go look. It's a clinic model, Okay, that was just because this is random clinics. Oh yeah, this vaccination disparities. That's another hybrid model with clinics, and people pick clinics and present to them, but it's a little bit similar to the one we did earlier, so I'm not going to look at that. So I think this one that I'm looking for is this is actually a quite nice one in a care context. This one is in the public domain. This one was built in one of our boot camps. So here we have a quite similar model in the sense that we have a depiction of physiological processes using stocks and flows, right? So we have people, individual patients whose dynamics in terms of their red blood cells related to conditions of anemia are evolving directly. And then we have prescribers that manage patients, and we're looking at the adoption of a protocol for patient management. And then we have these prescribers, sort of data on the outcomes for particular prescribers and data across the entire system. And this is for a set of dialysis patients based on a very nice model that Jim Rogers and Ed Gallagher have implemented at the Mayo Clinic for managing dialysis patients' hemoglobin levels. It's basically loosely based on that, but it's not the same model. So here we have providers with different sets of patients, and this color indicates the sort of the status of the patients. I think providers down here, and have patients who are going into various. So a given patient over time, their hemoglobin levels are shown here, and they're classed into one of a set of categories of whether they're safe levels or whether they're viewed as dangerous levels. Here we can look at sort of various outcome measures associated with the patients. What percentage of patients are viewed as sort of being under control according to certain and this is epoprotein cost, I think, per patient per week, average prescriber utilization, selected prescriber cost per patient, and hours required by the prescriber for assigned patients per week. Mayo Clinic was interested in this model because it had the promise, and it in fact delivered on, being able to simultaneously, and this is a striking thing, the actual model behind here, which is not the one you're running, but the actual model behind here was able to simultaneously simultaneously improve quality of life of patients by having them better stabilized in terms of their red blood cell levels, better able to improve their longevity by having them live longer because they had fewer adverse events because they weren't going up and down in terms of their hemoglobin levels. It was able to lower costs per patient. It was able to lower the amount of time required by the doctor to manage each patient, and able to lower the amount of drug required. And that goes along with cost. This is one of the most costly drugs in the formulary. So this is a system dynamics model that they use to sort of optimize patient management within a patient. And what we've done here is taken a stylized representation, put it together on a network of prescribers and patients, and use it to summarize the sort of measures that would be used by Mayo Clinic or other providers to sort of summarize their patient population. Part of the goal here was to examine the effect of different measures in terms of capturing some of these gains, the degree to which they really captured the gains from prescribing this. But a lot of of using this new protocol, but a lot of the goal was to try to understand the impact of diffusion of this new protocol on these various aggregate measures the provider would use to view adequacy. So, for example, on a percent of patients under control, or the costs associated with this, et cetera. So, to what degree could they take a model and go to their provider and basically say, look, we could potentially save a lot of costs, lower the amount of time required by the doctor, and lower the and enhance these outcomes that they have to report to a centralized control system with the percent of patients under control. So the idea was to sort of have different scenarios they could take and say, look, if you were to adopt this thing quickly, we would tend to see these sort of benefits within this period of time. So this is a model of, in a care setting, of patients under control of doctors. And as I recall, I think the doctor actually, these prescribers are actually making decisions for the patients. They're updating the dose for the patient over time, and you're seeing the impact on the patient. This is some of the dosing here. So this is kind of representing how does a provider make a decision. You could see here for the prescriber in this update current dose function, if they use the old protocol, this is how they would decide things. If they're using the new protocol, they just use a steady dose. And then looking at the outcomes for the whole organization, for that provider and for that organization. So here, each patient is using a model associated with a hybrid representation of dynamics within patient, just like the model the Mayo Clinic is doing, but we're able to capture the impact on aggregate statistics. And you notice if you click on a given prescriber, it shows their patients right now. Here they've, I think, all gone to the new protocol, but we can get it to show us, for slow deployment, sort of whose patients are under control, et cetera. So I'm going to fill this in and let it evolve over time. Over time, I think patients start in pretty good shape, but then they start to become less well under control. And after a few weeks' time or a few months' time, some of the prescribed here are, have patients, they have a mix of patients, some under control, some less than, and the patients not under control are requiring more of their time. By contrast, these, okay, it's green. I'd have to check what that means. This is better under control. Some of these are, I guess, less. Oh, that one's green now too. Oh, I don't know. Okay, yeah, these are less favorable. So here we have this multi-level structure. Okay, is that helpful? Yeah. See that? Okay. Now let's. I'm still looking for this other model of hybrid dynamics. I think it is not available here. I'll see if I can find it in a separate set I have that we share in our boot camp on machines only. This is the anemia and agents. It's ABM Clinic model. That's it. Okay. I don't know that I've run this in AnyLogic 7 before, so it might or may not run here. Let's give it a whirl. Okay, so here I'm going to run this model. This model, nope. Okay, no go. Okay. Give me okay, initial number of agents. I see. Fine. Catch that to that. Okay, and there we go. Okay. Okay. Okay, well. Okay, initial number of agents is from double to int. Oh, of course. Yeah. I'll just see if I can run this. So in this model, we have a kind of conceptually similar situation to what we had where people come in for care from a population. Here we have a single person population that doesn't make sense. Okay. I think I'll do right. Okay. In any case, the basic idea can be shown. We have people coming in from the population, and they come in from the population to this. Yep, there's 350 people in the population. I don't know why they're not shown. They come into this clinic here, and this clinic is staffed by a variety of individuals. So we have this care process based on a real-world care process for a clinic with whom I was collaborating. And within this care process, there's a set of clinicians, a set of interns, and a set of rooms. And when people present for care, they are routed between these different rooms, and they're seen in each of these rooms. In order to be seen, they have to be paired with a clinician and an intern. And then they can be seen and treated. They undergo a history physical up front, and then you can see them presenting for care. So they actually move physically around the facility when they present for care. So this is an example of a type of discrete event modeling where there's physical movement captured. I think it's familiar to many of you, but for those who have not seen it, if we go to this, what we'll find is, to take a look at the actual model, we'll find that there's a network of paths delineated here over which people can move. And when people come in, they go to the waiting room, and then they'll move up here, and their actual movement is captured through the facility. So the fact they move at a certain speed, the clinicians come and they will go and they'll go to a room and they walk out. All that sort of movement is captured along these paths, and that allows you to assess the impact of facility layout, among other things, on the throughput, how many people we can get in and treated per hour. So this is an example of a model where we have not only resource pools, but where we have physical movement associated with the facility. Okay, any questions on that or any questions on hybrid modeling before we close? Because it's a big topic. It's a topic that's, I think, of great interest with AnyLogic in particular, and I'd be glad to answer questions about it in general. These are just a few of the strategies you can undertake. I haven't shown you SD alone with DES, for example, and I haven't shown you, ABM, DES within an agent or something like that. So I haven't shown you all combinations, but I've shown you some. So any questions on hybrid modeling in AnyLogic? No? Just trying to think if I have any sort of final words to say on the subject. I think you've seen a lot of the essential mechanisms when I showed them to you for flowing in here, for individuals in an ABM becoming part of a DES, for a SD model to summarize things from agents. Those are all important sort of examples. Okay? No one has questions then? Right. Okay, that's a good question. So the answer to this will be a little bit different in AnyLogic 7 and AnyLogic 6. I created this in AnyLogic 6, and I did so using a mechanism called polylines. Okay? Polylines in AnyLogic 7 are used to delineate the sort of movement paths of individuals. There's a very nice training example that AnyLogic used to have, but I believe they no longer have it. But it's called the ophthalmology one. I'm just going to search to see if there's an ophthalmology training example referred to here, because if so, it would be great for discussing this exact issue.
Would this be found in the discrete event simulation modeling? Because it makes me think of the processes.
That's right. Yeah, it's discrete event, and it's I thought it used to be readily available as part of this, but I just don't see ophthalmology clinic here. The basic deal, though, is that you delineate paths and resources, paths and locations. So, for example, you'll say that this is the reception area. These are treatment rooms, and by putting sort of these bars between them, you can essentially say those are, whatever rectangles these cross should be treated as the treatment rooms. So if we go and we look at room resource pools, we'll see that that it's defined by this is okay. So this is the rooms, and this is a more sophisticated version of the model. Sorry. So it doesn't even make it as clear. But the basic deal is that you can basically say these are the resource rooms associated with a given resource. So in other words, if you have a fixed resource like a room, it's denoted by these rectangles. Okay, and then and you can do that for the various rectangles, and then you can specify these paths which run through the facility, which represent travel lines, and those paths link in at these sort of juncture points with subpaths going to each of these rooms. And AnyLogic will actually take care of all the routing from one area to the other. So, for example, here we're moving to a treatment room, and this is an operator, AnyLogic, and here you move to a specified destination specified by this. Generally, often it will be a particular resource that has been seized. Because this model is more advanced, I'm actually going to open here the ophthalmology example. I think I actually have it on my computer, and I thought I did. Okay, maybe I don't. But the basic idea is that you'll tell it, okay, I want to move to a certain. So you'll seize a resource, like you'll seize a room here, and then you'd say move to the associate seized resource, and that would move you physically to that resource according to the specified lines here. Now, AnyLogic 7 has moved beyond this. AnyLogic 7 has a large, sophisticated markup library here where you can put in various components into your model to indicate various resources. So, for example, you could specify a path over which people could travel, and you can specify various types of nodes, for example, rectangles for rooms, and you can specify walls, etc. So you can actually build up a sort of a representation of a facility from that. In AnyLogic 6, it was simpler. You had polygons, and you could tell, and AnyLogic could take care of routing someone from here to a treatment room, to a selected seized resource. And similarly, the doctors would have a home resource associated with them. So these clinicians would each be associated with this pod 1 room as their home node. So you'd have a resource associated with home nodes to which they'd return. If you're interested in this, I have very detailed lectures on the subject that are online that really spell out both the logical function of this sort of model, and it goes through a very detailed, simple example based on the ophthalmology case, where I explain the logical function and I explain how that's linked in visually, step by step. So I'd suggest you look at that, okay? It's in my videos. Okay, any other questions? Any other questions?
Well, I guess I have one.
Yeah.
So AnyLogic, you said you built this up in AnyLogic 6 and had that nice ophthalmology example. Does AnyLogic 7 make it easier?
Yes, it makes it easier. So it makes it easier through the use of these markups. And there's some other features in the discrete event modeling in AnyLogic 7 that are attract. It added some extra flexibility without complicating it much. But I would say that it was pretty good in AnyLogic 6, and I think AnyLogic 7 is a little bit better yet. The ophthalmology example I really liked, and that's the one I feature in my online videos on the subject, where I systematically explain the sort of the various operators and then give it a little example where they work. And I suspect there are similar models here. Like for the enterprise library here, there are these various examples, and I wouldn't be surprised if there's one that would be appropriate. But I'd have to look through it. And examples from the Big Book of Simulation Modeling, and may also be there's particular desirable ones there. Okay. Yep. Okay. Sure. Other questions? Yes, Rodrigo.
I know that it's possible to read from an Excel file or whatever the
Yes.
coordinate points.
Yes.
And you can connect them with lines.
Yeah.
But I know that agents will move through polylines.
Yes.
So can you transform those lines in polylines and make for example, if I want to simulate logistics movement, like
right.
trucks moving around a bus.
Yes. Yes. So you're saying, can you dynamically configure where these lines go to?
Mm-hmm.
I've actually done them. So I had a student in one of my classes that did a model with trucks moving around, and I remember thinking about this issue, but I think he may have used a static layout of the lines rather than reconfigure them live. But he was able to move around quite sophisticated ways around that. I don't think he had lines being added dynamically, and when I checked in AnyLogic 6, that wasn't possible. Maybe for 7 it is. I don't know though.
So that you say that he has to create the whole polyline with the paths, and after that he assigned the agents to the polyline?
He assigned, so then the agents could travel via the polylines, but he actually had a shortest path algorithm that routed them from one place to the other. Because I'm trying to remember, because he was not doing it DES, he was doing it purely agent-based, so he wasn't making use of the AnyLogic sort of routing that's provided in DES.
And he has to write the code for Dijkstra.
Yeah, Dijkstra algorithm. Mm-hmm. Yeah, exactly. Which is very easy. I mean, he did it in an hour or something. He's not a computer science student, but it's a very simple algorithm to code, actually. Okay. Any other questions? So in AnyLogic 7, entities and agents are merged, and I suspect because of that, you could probably route agents in very sophisticated ways on networks in a way you weren't able to do with AnyLogic 6. And I wouldn't be surprised if you could do it dynamically. You could change the network, but I'm not sure about that. Okay? Other questions? Okay. Great. Okay.